Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Hi friends, I'm excited to have here today Dimitris Papailiopoulos, who is a postdoc at Berkeley and got his PhD from UT Austin. Dimitris is a really interesting person because his work intersects three fields that are often not intersecting. So distributed systems and machine learning, which I care a lot about, but also coding theory. So he's bringing these three kinds of ideas together, providing new kinds of theoretical understanding for a lot of different algorithms, methods, and also some practical techniques in these areas. And today he's going to talk a little bit about his recent machine learning work in the area as a postdoc at Berkeley. So welcome. Thank you.
Great. Thank you so much. It's a great honor to be here. We can have this be as much interactive as you like, so please ask questions during the talk. So we'll start, and we will see that there's many problems in real life that are solved by machine learning algorithms. And we will see that in many of these cases, we would like to scale up our solutions for data sets that are high-dimensional and have lots of data points. And a good idea to do this is through parallel and asynchronous algorithms. So whenever I say that an algorithm is asynchronous, I will basically mean that it's a shared memory system with multicores where I try to have my processors not talk to each other as much as possible so that they maximize the time that they compute. Now we'll see that there are some race conditions and delays between different cores in these asynchronous algorithms that create theoretical and challenging and practical challenges. And the two main things that I will talk about here, first is a new framework for understanding and analyzing these asynchronous algorithms. And the main idea of this framework is that you can basically view an asynchronous algorithm as if you were running the serial counterpart on noisy inputs. And this is going to be a combinatorial noise that will capture the effects of core asynchrony, where you can have memory overrides during reads or writes, or the different delays between different cores. We will use this very simple framework to analyze some traditional machine learning algorithms and derive some new ones. And then we will see that there might be some issues with asynchronous algorithms. There are some problem cases where these conflicts between different cores can create an issue with respect to the algorithmic progress with some of these learning algorithms. And the second part of the talk will be a conflict-free parallelization scheme for asynchronous machine learning, where we are essentially able to avoid all possible conflicts, and we can have our algorithms be as much asynchronous as possible. And then at the end of the talk, I will focus on some ongoing and future directions that lie on the intersection of machine learning and systems. So first of all, why machine learning? Why is this a useful area? Well, there's many problems in real life, starting from automation and robotics, from driverless cars to machine vision. There are machine learning algorithms that are running in the background. Then recently, there's been lots of efforts with respect to drug discovery and healthcare where machine learning algorithms are used. Or whenever you're using Google Now or Apple Siri, there is a machine learning algorithm that's essentially figuring out what you're trying to say to your mobile phone. And somehow the more archetypal application of machine learning is recommender systems, where you log on web pages like Amazon and Netflix, and you get recommendations according to your previous purchases and your similarities to other users and so on. So now the question is, how do we tackle all of these different problems? And the idea is that we usually do this by formulating a mathematical or optimization problem. So for example, maybe you formulate binary classification for machine vision, or topic modeling, or matrix completion for recommender systems. Or maybe you'd like to train deep nets, or you would like to do a spectral analysis, and so on and so forth. And the interesting thing with respect to all of these problems is that a first way of attack is to basically try and solve them using an Über-algorithm. And this Über-algorithm is none other than the stochastic gradient descent. And usually the way that this works is you have a bunch of data points, and you have a loss function that is associated with each data point. And the loss function Fi will tell me how good the current model X is with respect to data point I. And our goal here is to basically try to find the model that minimizes these losses. And there's a very simple idea that dates back to the 50s and 60s that essentially says that maybe what you should do is sample data points at random and locally optimize for your model. So this is basically SGD, stochastic gradient descent. And the way that it works is that you start from an initial model. You sample a data point and you compute the gradient of the local loss. And you take a gradient direction according to that particular loss function. And here gamma k is going to be what is sometimes called the step size or the learning rate. So let's see a very simple example of stochastic gradient. So let's say we're in the binary classification case where you have two kinds of images. Let's say images of cats and dogs. And you would like to train a separating hyperplane that if you feed it an image of a cat or an image of a dog, the hyperplane can tell you whether it is an image of a cat or a dog. So the way that stochastic gradient works is that it samples one of the data points, and it goes to the model and reads a subset of the parameters of the model. So it will be the case in several applications that we will only have to read a small subset of the parameters. And then what we are going to do is compute the gradient of the local loss associated with that data point. That is essentially going to tell us how good the current model is with respect to the image that we sampled. And then we will go back to the model and update it according to the gradient direction that we computed. And the model will get better. And you will iterate this process again and again until you're happy with the model that you have at hand. So this very simple technique comes with different names and different flavors. So you might have heard it as the perceptron algorithm or the backpropagation, or even the LMS filter are essentially the same algorithmic technique. And this has been around for quite some time because it's a technique that is robust to noise. It is simple to implement, and it has a good learning performance under several learning assumptions. And it also has a very small computational and memory footprint that makes it ideal for large-scale data sets. Now, the interesting thing is that even this very simple algorithm can take hundreds of hours to run on large data sets. So for example, at Google, when they run stochastic gradient or variance of stochastic gradient, it can take up to hundreds of hours to train a good model. So the question here is how we can scale up stochastic gradient descent and how we can do this by parallelizing it. And let's go to a very simple example where we just have, instead of a single processor, now we have two CPUs. And here on my bipartite graph, I have data points and shared variables. Whenever you see a link from the left to the right, it basically means that this data point is a function of that particular variable. So in this case, I have my two processors sampling two data points from the left. And it so happens that there's no conflicts between the read and write accesses that these processors will have to do, which basically means that they are not sharing any variables on the right. So these data points that were sampled are not sharing anything on the right. So in this case, in this very simple toy example, it would be as if I ran two iterations of stochastic gradient in a single time slot. So you would essentially get a speed up exactly because there's no conflicts, and this is like running two iterations. Now, it will be the case at some point in the execution that the two different processors are going to sample data points that are sharing some variables. So here, for example, they sample the first and second data points. And they're sharing, they're conflicted on one variable. And the main question is, what should you do here? And there's two paradigms that you can follow. The first paradigm is essentially saying that maybe what you should do is coordinate the different cores so that they basically figure out who has to go first. Or what you could do is you could basically lock a subset of variables while a processor is trying to read and access these variables so that no other processor can access them. So this is the first approach. And the second paradigm is to basically say that you don't care. Like basically have your processors operate on the shared memory system as if they were the only processors on your system. So this would be the approach of just not caring about conflicts. And there's obviously lots of work on parallelizing stochastic gradient that even dates back to the 70s and 80s. And there has been lots of recent work up until 2011. And the bulk of this work focused more on the idea of coordination or locking variables while you're trying to access in parallel the different variables of the model. And one of the issues of coordination and locking is the fact that it can be the case in practice that computing the gradients can be cheaper than basically having these locks and these coordination mechanisms. So the main question here is, why would you coordinate and lock? Like, is there something that you're getting from it? And in 2011, this gentleman here came up with an asynchronous lock-free implementation of stochastic gradient, which they call Hogwild. And the way that Hogwild works is that it essentially, you let each processor in the system operate as if they were the only processors. So each CPU will sample a data point, read and write on shared memory, as if no one else is trying to access the shared resource. And they, they had lots of experiments, and they showed that the speedup that you get when you use Hogwild versus locking or coordination approaches can be much better. So here, for example, in this curve, the blue line is the speedup of Hogwild versus the number of threads. And the two dotted lines, they either follow the coordination or the locking approach. So basically, getting rid of all coordination and locking gets you significant gains with respect to the different approaches. And there was significant impact of Hogwild both in industry and in theoretical research. So for example, Google Downpour SGD uses variants of Hogwild. And also Microsoft's Project Adam, which is a learning system, is also using Hogwild. And it has renewed a lot of interest in trying to develop and analyze synchronous and lock-free algorithms.
So this Downpour, aren't things dense there? So how do you deal with, if everything's dense?
Yes, that's right. Well, they still run Hogwild, and it still works well. And even if you have dense updates, sometimes it still works well. And there is a good reason why this works. Maybe we will see it in the following slides. But you can still apply the algorithm for dense updates. And it only scales up to a specific number of threads. It doesn't scale to as much as you like. So yeah. So there are some challenges in these Hogwild type of algorithms. And the challenges are the following. So again, we're in the multi-core shared memory setup. So maybe you have processor 1 trying to access a subset of the variables in the memory, and another core comes and it's sharing a subset of variables while reading or writing. And maybe you have another core trying to sample, update, and write in shared memory, but it takes too long, and maybe many updates happen at the same time. So the two main issues that Hogwild algorithms have is the first thing is that the updates of a single processor can be stale, meaning while a processor is updating and processing a single sample, many things might have happened in shared memory. So by the end of the execution, maybe that update is way too old. And the second issue is that you might have overwrites of results. While a core is processing a single data point and is trying to access a subset of variables, maybe these variables change during the data processing of that particular core. So these two issues is essentially what makes us depart from the classical analysis of stochastic gradient. And the question here is, how do we analyze and understand the performance of these log-free parallel schemes? There has also been lots of work in trying to understand the convergence rates and the performance of these algorithms. And one of the issues of prior work is that they have been using simplified models with respect to reads and writes, so that they render the analysis similar to the serial case and have it be more tractable. For example, one of the assumptions in prior work is that you have what we call consistent reads, in the sense that while a core is accessing a subset of variables in shared memory, these variables will not change by other cores, which is something that might happen on the opposite side in practice. Like you can have reads that are not consistent. And the other issue is that the authors there analyze a single coordinate update of stochastic gradient, which means that for each sample update, there's only one single variable that is being written in shared memory. So the question here is whether we can develop an intuitive and general framework for analyzing and understanding the performance of these log-free parallel schemes. And the main idea that we've been essentially working the past couple of years in the AMP lab is basically view these algorithms, these asynchronous schemes, as if you were running the serial algorithm on noisy inputs, where this noise is going to exactly capture the effects of core asynchrony, the memory conflicts and the core delays. And the question is, how can you prove convergence and speed up guarantees for these kinds of schemes? So let's see. Now, the idea is that we'll try to frame Hogwild as a noisy version of the serial stochastic gradient algorithm. So let me just define as SK the kth sample data point. So let's assume that we have an atomic counter that every time you sample a data point, the counter is going to be +1. So SK is going to be the kth data point that the processor is sampling. And a fact here is that because you don't have consistent reads, what the cores will actually read from shared memory is not actual iterates xk. They will read noisy iterates xk hat. So xk hat is what the processor that sampled the kth data point is reading from shared memory. Now, what we will assume here is atomic and successful writes, which means that every time a processor is trying to, let's say, commit +1 in shared memory, this +1 will be recorded in shared memory at some point in the execution. Now, because of atomic writes and the commutativity of addition, what we will see after T updates in shared memory is the following. So you'll see the first iterate, x0, and the update vectors that the cores try to commit shared memory, which is gamma, grad, fs0, and so on and so forth. And although the writes might have happened in a weird intermingled way, it doesn't matter because you have commutativity of addition. And you can basically represent it exactly using this equation here. And the question now is, since you have this representation of the contents of shared memory, how do you say something useful about the algorithmic progress of Hogwild? And the way that we know how to do this is by just defining iterates. So I will define as the first iterate the normal thing, x0 plus the update of the first core, and so on and so forth. And now what we get is a recursive formula that is very familiar to the optimization literature. And there's two interesting things to observe here. So first of all, this formula is basically saying exactly the same thing as the long line of characters there. So if you expand it, it's going to be exactly the same thing. And there's two interesting things happening here. So first of all, what you essentially get is the evaluation of the gradients are going to be on the noisy iterates. So this is the only difference with respect to serial stochastic gradient. So instead of reading x, here you read x hat. And the other interesting thing is that the iterates here are phantom and fake in the sense that apart from x0 and xt, nothing else really exists in shared memory. So you can't really put your hands on the intermediate iterates. But that doesn't really matter because all you need to prove convergence guarantees is just x0 and xt, the first and the last iterate. Now, the two main questions here is where does this noise come from in the noise evaluation of the gradients? And how strong is this noise and whether it can change the convergence properties of these algorithms? So to understand the effects of core asynchrony, what we will try to do is just see a very small example of three processors and a data set that consists just of 3 samples. So here, again, I have my data points on the left, and on the right, I have my variables. And whenever you see a line from the left to the right, it just means that this data point is a function of that variable. Now, what I will do is I will decompose the parallel timeline into a serialized processing timeline. So in that timeline up on the left, what we basically see is the time that the processor starts reading something up to the time that they're done writing in shared memory. So if we break it down into a serialized timeline, what we'll see is that the first CPU comes and samples the first data point. It tries to read and write from these variables in shared memory. And then you have the second processor try to read and write from another subset of variables in shared memory. But it so happens that they're sharing this second variable. So this variable on the red is going to be my conflicting variable, which is going to be basically what I mean by noise. And then you have the third CPU coming and sampling the third data point. But because it's completely irrelevant to what is happening in the rest of the data set, then although it's a concurrently processed sample, there's no conflict, so everything is fine. So to the question, what causes asynchrony noise? The answer is the noisy reads of the coordinates in the overlap between differently concurrently processed samples. So these red variables are exactly my noisy variables. And since I have that, what I can do is go back to the serial stochastic gradient iteration and say that, OK, instead of evaluating everything at the current model, I have this additive noise on the variables that are in the conflict between the different processors. A thing to note here is that this noise is going to be combinatorial in the sense that you will have a random support, which we'll see where the randomness comes from. And the coordinates in the conflict can be as noisy as possible in the sense that we're not assuming any generative model behind the intensity of these coordinates. So they only depend on the intensity of the gradient computation. Now, the thing to note here is that asynchrony is not a big issue as long as you don't have conflicts. Only whenever you have conflicts between concurrently processed samples, then you might have an issue in the algorithmic progress of these algorithms. So when do we have conflicts? What we can do is look at the dataset matrix, the data points variables bipartite graph, and generate a conflict graph between the different data points. And here I will link two data points if they share at least one variable on the bipartite graph on the left. And a very simple statement here is that if you have two samples that have been uniformly sampled from my dataset, the probability of them being in conflict, the probability of them sharing at least a variable, is going to be proportional to the average degree of the conflict graph. Delta will be the average degree of the graph on the right, divided by the number of data points, n. So if the sparsity is small and the number of data points is large, then this probability will be small. Now, an observation here is that if you don't have way too many concurrently processed samples, the number of conflicts, the expected number of conflicts per sample is going to only be constant. And a lemma that we have here is that if you have a constant number of conflicts per sample data point, then asynchrony noise, these conflicting variables, are not essentially going to cause anything in the algorithmic progress of Hogwild. So what this translates to is the following theorem. So the main result will state the following. The only assumption that we will use here is that there's not more than tau samples that are concurrently processed with a given sample. And a way to think of tau is as a proxy for the number of cores. So what the main theorem says is that if you're not using way too many cores, then asynchrony noise is that small that essentially the performance of the log-free parallel algorithm will be the same as the performance of the serial algorithm in terms of the convergence rates. And this is assuming convex functions. Now, two things to note here are the following. So first of all, sparsity for these kind of theorems is key. And the question is whether it's a realistic assumption. There are several applications where sparsity can be naturally found. For example, in matrix completion and matrix factorization, in graph cuts, in topic modeling, or whenever dropout is used, sparsity is inherent in the problem. And the second note here is that if we try to compare this result with the prior work on Hogwild, what we get is that we can essentially waive all of the prior assumptions on the read and write models. So there's no assumption on consistent reads here. And we analyze the full gradient update version of the algorithm where we don't only have a single update in shared memory. And we also get an improvement in the number of cores that we can use in the system. And a question to ask now is that, all right, this noisy framework tells a nice story for Hogwild. And they
Next time I can ask a couple questions.
Yes, please.
What's the dependency on tau on the theorem is the first question.
So there is a constant factor that is multiplying the convergence rate. That constant factor can be as close to 1 if tau is small. So there's like 1 plus, let's say, 1 over tau times the sparsity of the problem. So the way that tau goes in there is that the higher tau is, the slower the convergence rates will be because you have higher asynchrony noise, essentially.
In a linear way, though, right? So
it's a little complicated. It goes in a linear way as well.
You not have bias here?
Yeah, you do have bias. Yeah. But the point here is that the bias is that small that essentially doesn't matter.
No, wait. It's a function of tau, right?
Yes. Yeah. So if you make the bias proportional to the bias of the gradient, then you're fine. That's essentially the statement.
So, but if your dependence is linear in tau, still trying to understand that, then what do you gain from parallelism? Because if I guess the point is the following. If tau is smaller than that, you won't see essentially any decay in the convergence rates.
So you will get, let's say, 1 plus epsilon of the convergence rates of the serial algorithm if you have a tau that's, let's say, smaller than this number. So essentially, you're not losing much by that much. If you go beyond that, it's a little unclear what's going to happen.
I see.
Yeah.
So what's the basic idea in the proof?
So the basic idea in the proof is that because you don't have conflicting updates too often, if you're not using these many cores, the chance of having a conflict is going to be extremely small. So the expectation of the variance that you're creating is going to be a small quantity. So you're basically trying to bound the variance that the bias that you're introducing in your parallel execution.
So couldn't I design an adversarial sequence of updates that actually causes a particular...
Oh, absolutely, yes, absolutely. So something that is key here is the fact that we are uniformly sampling the data points. It could be the case that you could pick a permutation that it could be extremely bad for this one. But in practice, we assume a random permutation or a with replacement sampling. Okay.
And you assume that the x's belong to a ball or something, so you can bound...
Yes, yes. So this is one of the assumptions that we essentially need, that the gradients are uniformly bounded because of exactly that fact. Okay, yeah.
So it seems like these are sufficient conditions but not necessary conditions, in the sense that, you know, even if sparsity wasn't true, it still could be the case that you get good convergence rate if it's the case that the gradients in some sense agree with each other over
Precisely.
And so perhaps, and maybe empirically you see that tau doesn't need to be so conservatively set, and maybe this is why you're saying that even in the dense case, it works with larger tau.
Absolutely.
And have you been doing any analysis on that?
Yeah. So 2 points. So this is only a promise on the lower side somehow of the transition, that if this is true, things are going to go well. This does not imply at all that things will go bad if you cross this. There are some examples where Hogwild works well on dense problems. And as you said, what really matters is that essentially the sample gradients have a small inner product. So something like a soft sparsity. If this is true, things in theory will go fine, essentially. Yeah.
So these results say only relate to the degree of sparsity of the connection, not to the strength of the conflict.
Yeah, that's true. Okay. So we, to make things easy in the computation, we assume that somehow all of the connections can be equally bad, which means that we are hurting ourselves because we could be possibly showing something better if we took into account the weights. But here we assume that as long as you have a single one conflict and conflicts, the same thing in terms of the conflict graph. But that is only hurting the bounds. Yeah.
So in the sparse setting, the lock-based or coordinate approach could also try to engineer itself towards optimistic transactions and other techniques. So this is a very nice result, but it doesn't answer the ultimate question, if you will, in the sparse setting, which approach should I take? Is that amenable to analysis, or is that still an empirical question?
That's the second part of the talk.
Thank you.
Yeah. Great. So the first sort of meta question here is whether this idea generalizes. And the reason why I like this noisy lens of asynchronous algorithms is the fact that you can use it for different stochastic optimization schemes. So you can also analyze the asynchronous implementation of coordinate descent. But you can also use it as a very simple recipe for designing new algorithms. So the two ingredients of the recipe is that you need sparse updates and asynchronous updates. So for example, we're able to develop a new algorithm for asynchronous and sparse SVRG. SVRG is a variance-reduced version of stochastic gradient, which essentially minimizes the variance of the updates. And what we do here is we take the classic version of SVRG, we do sparsification, and then we do asynchronous updates. We analyze the algorithm using the noisy lens. We saw some performance guarantees. And in practice, what we get on a 16-threaded implementation, when we compare to the serial dense version, we can get up to 4 orders of magnitude faster result. And that is mainly because we do the sparsification step. And when we compare to the serial sparse algorithm, what we developed, we're on an 8x speedup on 16 threads. The other interesting thing about the noisy lens is that we have also applied it on a problem that has nothing to do with continuous optimization. So we developed a log-free correlation clustering algorithm. So this is a variant of graph clustering. The problem is completely combinatorial, and the results that we saw are with respect to a sort of combinatorial approximation ratio. And again, in implementations, what we see is that by using a 32-threaded implementation on Scala, we can cluster with this simple algorithm, billion edge graphs in under 10 seconds and get a 12 to 15x speed up on 32 threads. So the point of this of the first part of the talk is that there's this very simple way of viewing asynchronous algorithms. It's useful for a set of stochastic optimization algorithms, but also for a combinatorial graph clustering scheme. Of course, the question is how far can this framework go? And one of the main limitations right now in theory is that we have this assumption on convexity and sparsity to establish speedups. But again, in practice, you have problems that are dense and you have problems that are not convex. So the question is how necessary are these assumptions and how far can we go in these settings? For dense problems, there has been some work by John. And essentially, I think the idea again is that if you have gradients that are concurrently processed and have small inner product, then things should be expected to be fine. But there's still, I think, work to be done in understanding these kinds of cases. But I think maybe a point that we should be making here is that since sparse updates are good, maybe a way to go forward is try to featureize inherently dense machine learning problems so that they can have as much sparse updates as possible. And the holy grail in this kind of the thread of my research is to essentially see whether we can establish some performance guarantees for Hogwild and log-free algorithms for non-convex settings. And we have some ideas of how to do this, and this is ongoing work. So any questions for the first part? Yeah.
Well, I mean, one obvious question is partitioning to try to improve sparsity.
Yeah.
Has there been work on that?
Partitioning?
Well, I mean, so each processor, say, for example, suppose it gets sets of points that never conflict because they're on one processor, and you don't go off processor too often, so therefore you reduce the number of conflicts. And
this is also the second part of the talk.
That's the second part of the talk?
I think so. Let's see. But I think it's the second part of the talk.
Sorry.
Good. So, but if, say you have a dense problem, and you can't featureize it so that the updates are sparse, right? Then maybe what that means is that actually it's okay to do the dense problem.
Yeah.
Because it has the necessary properties and we actually don't need to featureize it. You can just prove that this works for the dense problem.
Yeah, I think that's an interesting, so this is interesting. And I also think there's a fundamental question of how parallelizable these inherently serial algorithms are. Whether, like, is there an actual fundamental limit that we can go beyond? I think this is like a very interesting question. So, and it could be the case that you could sparsify it, get a good speed up, but then the learning properties could be worse. So it's an interesting trade-off. Okay, great. So in the second part, what we will essentially see is that we would like to try to avoid conflicts using a graph partitioning tool. And this is a new framework that we call Cyclades for synchronous and conflict-free machine learning. And the idea now here is that you might have some limitation in terms of Hogwild types of algorithms. First of all, conflicts for some particular problems can lead to significant errors in the algorithmic progress. You might also have bad cache locality because of the way that the read and writes are right now, so they're completely random and there's no structure. And also, even with this very simple noisy lens, you still have to reapply it for different applications, and you still need to tailor it to different problem setups. So the question here is whether we can go beyond Hogwild algorithms, find a large family of machine learning schemes that look similar to how stochastic gradient works, and whether we can parallelize it in the asynchronous and log-free setting, at least as much as possible, and whether we can take it a step further and say, okay, maybe now what I can do is completely avoid conflicts and have the asynchronous algorithm being serially equivalent to the serial version of it. And maybe you can also take it a step further and say, can we be faster than Hogwild? So the answers here are going to be a partial yes. We have a new framework, which we call Cyclades. It is going to be asynchronous and log-free, similar to Hogwild. It's going to have good cache locality, and it is going to avoid all access conflicts with respect to read and writes in memory. And the thing that I really like about Cyclades is that it comes with a black box analysis, in the sense that if the algorithm fits the particular family of machine learning algorithms, then I can promise to you that you will get a speed up without having to reprove essentially convergence rates or anything like that for the parallel algorithm. So again, the motivation is that you have many different algorithms that look like stochastic gradient, And the way that these algorithms work is that you have a set of functions or a set of data points. And the way that these data points interact with the variables are through some sparse connections. And these algorithms, they go through the data points in a randomized way, and they read and update and do local computations. So can we have a general lock-free parallelization framework that is conflict-free? It has better cache locality than Hogwild, and it also comes with a black box proof machinery. And to do this, we have to go back to the graph of conflicts. So again, I have my data point variables bipartite graph. You see a line if there's a dependence between a variable and a data point. And I will just again create my conflict graph. Even if you have a single conflict on the left-hand side, you will put an edge between two data points. And there's a very beautiful and interesting theorem that was established a year and a half ago that says the following. So now you can forget about machine learning algorithms. This is a very nice graph theoretic statement. So give me your favorite graph that is defined on n vertices. And just tell me the max degree of this graph. Now let me sample n over delta vertices from this graph. So n is going to be the number of vertices. Again, delta is the max degree. If you let me sample n over max degree, what will happen is that the sample subgraph is going to essentially shatter into very small connected components. And you can actually establish that the largest connected component is going to be of size logarithmic. So you give me your favorite graph. I sample n over max degree. The largest connected component is going to be at most logarithmic. Why is this useful? Well, now you can use it for parallelizing algorithms that follow the random access patterns that we saw earlier. And what you can do is you can randomly sample from the conflict graph and then allocate connected components to different cores. So this is essentially the idea that Cyclades is using. So what it's doing is that it is looking at the data point variable graph. It's going to sample a number of data points, and then it will compute connected components. Now, these little blobs here, the little dots inside the connected components, are going to be the updates of the algorithm. The note here is that there's no conflict between different connected components, meaning that the updates of different connected components talk to different subsets of shared memory. The other point to note here is because of this graph theoretic statement, the size of these components are going to be small. So if you sample lots of vertices and the size of the conflict groups are small, the number of conflict groups is going to be large, which is going to be good for parallelization because you can basically allocate them across different cores. So this is essentially what is happening in the second phase of Cyclades. We take the connected components that we computed in phase one and basically do a fair load balancing so that the weights are essentially the computational effort is uniformly allocated across different buckets, different cores. And then for the last phase, what will happen is that each core will essentially go through the allocated connected components, and then they will just do the updates in shared memory, read and write. And the interesting thing here is that this will happen asynchronously and without conflicts. So in the last part, the stochastic updates part of Cyclades, there will be no coordination, no locks in shared memory, and everything can talk in the variables in the model without having the fear of overrides. So essentially, the last part is as if you were running Hogwild without any locks, without any conflicts. Now, the 3 points to note here is the first is that for the last computation part, the cores operate asynchronously. There's no locks. We don't need any locks because there's no contention in shared memory. There is going to be access locality, better cache locality, because cores will access the same coordinates in the model again and again. And also the communication is minimal because you essentially only read and write once per sample batch from the shared state. Yes?
Maybe you'll get to this, but can't you have a heavy tail on convergence? There's no guarantee these things will converge at approximately the same time.
Yeah. Great. So this thing now will have to be repeated. So you sample one batch, you have to sample another one, and then you have to repeat this graph processing, pre-processing tool. And the main question here is, like, does this thing really scale? Because you have this sort of data partitioning component that could be easily more expensive than the last part. And the main idea here is that obviously the last part, because of the fair allocation, is as good as possible. And for the first part, what happens is that you really don't need to construct a conflict graph. The only thing you need to do is have a good estimate for the max degree, and then essentially allocate across different cores and compute the connect components. Yes?
So if the original graph just so happened to be consisting of p connected components, wouldn't the Cyclades essentially shatter those connected components and distribute them across the cores, potentially not taking advantage of what's inherently embarrassingly parallel already?
Yes.
So then if they weren't embarrassingly p connected components but loosely connected components, couldn't there be potentially much better partitions by doing a graph partitioning?
I think they probably should, yes. So there is a version of Cyclades where you can essentially do more dynamic version of connected components where you build them up until they're too big to handle, and then you stop. If
there's sort of cliques of variables that really are talking to each other a lot, they shouldn't be shattered.
Yes.
And this would potentially shatter them.
Yeah, that's true. So the way that I present this now, it's oblivious to this sort of more amenable structure to parallelization. So this is more sort of a general purpose technique.
So I'm still a little confused for phase one.
Yeah.
Why you don't have to form the graph?
Okay, so the only thing you need to look, so the important part here is you need the connect components.
Right, so you still have to form the graph between the nodes that get selected.
So you don't really need to do this because the bipartite, if you sample vertices from the left of the bipartite graph and you compute connect components, you can essentially prove that this is exactly equivalent as compute connect components on the conflict graph. So the only thing you need is the bipartite graph, which is essentially your data set.
You still have to compute, I see, so you don't form the graph, but you still have to go from vertices to features to vertices. So you have to have an index for both sides to be able to do that.
Yeah.
Which is normally you don't have at that point.
Yeah. And the point here is that if the first graph partitioning phases are fast, we're good. And what I try to convey is that if we do this very simple sampling and graph partitioning where we don't really create the conflict graph, the cost of the first part will be less expensive as compared to the second part. So you can use these two essentially very simple lemmas to basically establish that under two restrictive assumptions. So if you have, so here we need sparsity. So sparsity is important here. So if you have sparsity, and if you're not using way too many cores so that the allocation is fair, then you can achieve a linear speedup with Cyclades. And the important thing is that you will get a serial equivalence guarantee. The output of the algorithm after t iterations will be the same as if you were running the same t iterations on the serial algorithm. Now, the useful thing of this is, so far I didn't tell you anything about the algorithm we're parallelizing here. As long as it fits this sparse updates family, I can basically provably parallelize it. Another question is how this thing performs in practice. And we have run several experiments. I will just show you two simple ones. So we have an implementation in C++. This is going to be on a 1 terabyte machine. And I'm going to show you a classic matrix completion algorithm and a graph Eigenvector SVRG algorithm that has been recently developed by Sam here and some collaborators of his. So for the first application, the graph Eigenvector computation, the way that the updates look here is that you can write it as you take the initial, the model that you start with, you reweight with a constant. You have a sparse gradient update, and then you add a constant vector to it, which can change after maybe a couple of epochs. The size of the problem here is going to be 1 million data points, and the dimension of the model will also be 1 million data points. And the point here is the following. This particular algorithm is going to be sensitive to asynchrony errors. And if you push the step size high enough, you're going to see divergence of the Hogwild algorithm. So what happens is if you compare the speedup so the red line here is going to be Cyclades. The blue one is going to be Hogwild, sort of the simple asynchronous log-free implementation of this algorithm. And in this case, we see a gain in terms of speedup that is up to 2x. And the reason why you see this is, again, because the conflicts due to asynchrony are going to basically overwhelm the algorithmic progress of that particular algorithm. So for these kinds of applications, maybe the point here is that we should be using more careful parallelization techniques.
Why are you not getting linear speedups here, since you have such few processors compared to?
So there's several issues. So
I guess I should ask.
So in this case, I think it was an issue of the updates being really cheap. So there wasn't much room for parallelization, essentially.
No, I mean, I'm saying, I'm comparing it against himself because they're all starting from the same point on the left.
Yeah.
So
yeah, I think the interesting takeaways here is that even sort of Hogwild that is expected to perform well, it is not getting the sort of promised speedups that you would hope for here, and it's because in this case the updates are extremely cheap anyway. Mm-hmm. So it seems that there's not room, at least in this implementation, for better speedups. Yeah.
Sorry, is this machine efficiency speedup, or is this sort of measuring time to get to a particular quality solution?
Yes. So we fix an accuracy. We let the yeah.
It's the latter one. It's not machine efficiency.
It's both. So the machine efficiency issue is with respect to the red curve, because you would still expect something better. For the second curve, because you have extra error in the execution. Great. So for the sort of more simple stochastic gradient experiments, we'll just see a matrix completion dataset, the vanilla movie lens, 10 million data points, 8 million dimensions in the model. We're going to use the regularized version of stochastic gradient. The way that the updates look are essentially similar to the serial version of stochastic gradient, but you also reweigh the updates to achieve regularization. Now, the interesting thing here is that we expect Hogwild to perform well because the conflicts are not there, and this is sort of exactly the algorithmic regime where we expect it to get good speedups. But the interesting thing here is that we can get a little bit of a gain, a 30% to 30% gain, just because of cache coherence and cache locality effects. And this happens because of the way that you allocate the updates. Cores are accessing again and again the same subsets of the variables in shared memory. To conclude this part, we have a framework for nearly asynchronous and log-free machine learning. This framework, Cyclades, is taking care of all of the conflicts, and it has a serializability guarantee, which essentially implies that you have a black box speedup guarantee for any algorithm that fits the algorithmic family of random stochastic updates. The open problems is that we have poor performance on dense data sets. If you have many outlying, let's say, data points that are very dense, then Cyclades will perform significantly worse than Hogwild. So the question is that maybe we should try to sparsify some of the dense data sets. Or what we could do is maybe do sort of a smarter partitioning according to similarity of data points, not just sparsity between data points. And we'd also like to experiment with GPUs, where we can push some of the cache coherence limitations away with respect to the sort of parallel CPU case. So this concludes the second part. Please let me know if there's any questions. Now, for the few minutes that are remaining, I will just briefly talk about some ongoing work on the intersection of machine learning and systems. And the two main sort of blocks of work that I have been studying the past semesters are essentially revolving around erasure codes and their use in distributed machine learning, and also the intersection of machine learning and systems. With respect to the erasure coded bit, I just want to put things a little bit in context. I got my PhD from UT Austin, where I worked with Alex Dimitris on fault tolerance that is optimized for distributed storage. We had some interesting theoretical work that also had some practical impact. We collaborated with Facebook and implemented our codes in their version of HDFS. And related codes were constructed independently by collaborators of ours from MSR Redmond and are currently used in Azure and Microsoft Windows. And for this part of my work, I was essentially focusing on the, let's say, intersection of erasure codes and storage systems. And the question that I had during my postdoc is whether we can use codes to go beyond fault tolerance and whether we can use them to essentially speed up some issues of machine learning systems. Now, an interesting application is the following. So in many cases, what we have, so let's say that we are in a distributed setup where we allocate tasks across different nodes, and we are running an iterative sort of algorithm. Let's say you run a training type of problem where you allocate training samples across different nodes. And in many cases, we operate under what is called the bulk synchronous processing paradigm, where a master node has to essentially wait for the slowest worker node to be done so that it can essentially reiterate the process. And the issue here is that if you have many distributed nodes, what will happen is that you're going to see the tail effects of the execution times. So you're going to have, let's say, 10% of the nodes being significantly slower than the, let's say, 90%. And the question is whether you can use some very simple ideas from coding theory to essentially speed up these kinds of issues in distributed computation. And there's a very simple idea that you can use specifically for linear functions. So let's say that the first machine is allocated with task 1, and the second machine is allocated with task 2, and I have a third machine that is computing the parity of the two tasks. And by parity, I mean just essentially summing the data points and computing task 1, let's say, plus task 2. Now, in this very toy example, with this very simple code, what you can get is that instead of waiting for all 3 of the machines, you can just wait for essentially any 2 out of all of the machines. So this way, you take care of one slow straggler node. And there's very interesting connections to sparse graph codes and how far this idea can go for different functions beyond just linear applications. And the interesting thing is that this idea in practice, so we have a simple OpenMP implementation. And on a 10-machine experiment for matrix multiplication, we can see up to 2x gains with respect to the running time by just using a very simple erasure code. And there's also another simple thing that you can do with coding. So something that is very useful in practice when we're training models in a distributed setup is that so you have your dataset and you give pieces of your dataset to different worker nodes. And each worker node is essentially training a local model. And this local model is aggregated, and the iteration of training models is repeated again and again. Now, for each different iteration, it is statistically better if the worker nodes get a fresh slice from the dataset. Now, if you do this per iteration, the issue is that you will have to communicate the dataset across the entire network per iteration. So this is going to introduce significant communication overheads. So can we use erasure codes to reduce some of these communication overheads of data shuffling? And the idea here is simple. If your worker nodes can cache some of the old information, you can use this information to reduce communication between different iterations. So for example, if I'm worker 1, and I have, let's say, data point A, and you are worker 2, and you have data point B, and on the second round, I need B and you need A, the master node will only need to transmit A plus B, the sum of the two data points, and not A and B. So in this very toy example, you reduce communication by a factor of 2. And again, in practice, we see that on a 10-machine experiment, on a very simple training task with linear regression, we're able to get 50% less communication when we compare the uncoded version of the algorithm with the coded shuffling version of the algorithm. So these two examples are essentially two indications that codes can be used not just for fault tolerance in distributed systems, but to also speed up some of the distributed machine learning tasks that we are interested to solve. And then something that I find extremely interesting is optimizing machine learning algorithms for different platforms. So something that we have been working on with collaborators from Berkeley and Stanford is what essentially happens when you're in a NUM-aware topology, where you're still in the single machine case, but CPUs are having a specific topology with respect to the memory slots. And in these cases, you have to be careful about how you're essentially allocating the data points because you have different costs in accessing different sockets in memory. So how do we optimize machine learning for NUM architectures? And something that has also been happening lately is Google has been thinking of bringing some computation from the cloud to the edge devices. So the question is, how can we do distributed machine learning on mobile phones? And now you have really strong hardware that comes with limitations, battery and heat limitations. So under these constraints, how can we optimize parallel algorithms for machine learning? So far, what we have been essentially looking at is general purpose, parallel and distributed setups and systems. And the interesting thing is that for all of these machine learning applications that we are looking at, the algorithms that we care about are concentrated around a very small ballpark of algorithms that have very specific access patterns and operate in a very specific way. And the question is that maybe we should be designing hardware that is optimized for these particular applications that we care about. And I would like to just conclude with the driving question for my research so far. The main question that I think is extremely interesting is how we can enable large-scale machine learning on new computational platforms. And my approach, especially in the 2 last years in the AMP lab, is to essentially try to design optimized machine learning algorithms by putting the system's design constraints in perspective. And what I think is also interesting is to maybe close this loop and design our systems and architecture so that they are tailored for the particular machine learning applications that we care about. And with that, I would like to conclude.
Any questions here? So, oh, sure.
I mean, naively, why wouldn't you think there's a limitation for the dense case? Like, just take one of these sparse cases and do a random rotation. It seems like you're just completely going.
So my claim is that there are some problem setups where the dense updates will work, but this is not a universal statement in the sense that I believe there will be data sets where you won't be able to do anything better than just using a single thread. But the only thing I'm saying is that there probably are data sets where dense updates should be fine. So there was a paper by John Ducci, I think it was NIPS last December, where they were looking at sort of dense versions of Hogwild. And they did show that there were some significant speedups for some problems.
Pedro?
So you said you were hoping to extend your results to non-convex problems. That sounds interesting. How are you going to do that?
OK, great. So the point here is the following. So the only thing that you care about in the asynchronous and parallel algorithm, the only useful bit that you can sort of say as a, let's say, theorist, is that you can get a provable speedup. Now, if you somehow religiously believe that the serial algorithm works well, for, let's say, training deep nets, and maybe it's hard to prove that it is actually working, but you really believe that it does, I think the interesting thing to do is transfer this belief to the parallel case. So if I promise to you that the parallel asynchronous algorithm will output a result that is as good as the serial algorithm, this is essentially closing the case. So that is the kind of thing that we're trying to prove for the non-convex case, meaning that the result that we're trying to establish is that even if you have non-convex problems, I will try to establish that the output of the asynchronous algorithm after t iterations will be close to the output of the serial algorithm after the same number of iterations.
But that's what seems, I mean, the noise could be enough to put you into a different basin of attraction, and then you have no guarantees whatsoever.
Absolutely. So so the guarantees that you can show are with respect to the iterates themselves. So we can show closeness of iterates, of models. Now, if your function is very weird and the really close models are thrown away to different basins, it could be the case, but you can't really control this unless you put some assumptions in the problem.
I think we should, it's time, so thank you very much.